A second aspect of our free radical chemistry is free radical oxidation. And this doesn't have any particular synthetic utility, but it's quite important for understanding the degradation of a number of materials. Autooxidation of ethers, so in the laboratory, diethyl ether uh, can lead to the formation of explosive peroxides. So ether is stored in light impervious containers. Typically, these are now aluminum screw top cans, occasionally still brown glass bottles, but those are usually shipped inside of a metal cylinder. And then laboratory practice these days is to date the bottle when it is opened and to destroy any unused material after a defined period of time, usually on the order of 30 or 60 days, and to keep the material refrigerated as well. Cleaning out old laboratories, one of the big hazards is the discovery of explosive peroxides when ether has evaporated to dryness and left these explosive peroxides as a percussion explosive residue. Autooxidation of many foodstuffs, unsaturated oils. If you've ever tasted rancid oil, popcorn made with bad oil will have a rancid flavor. Foods that are fried or preserved with, or rather contain high lipid content, are subject to autooxidation. And then a subset of this is the degradation of pharmaceuticals. Autooxidation reactions in particular can be difficult to control and difficult to recognize, and may go long periods without being observed, and then for variables that are not well controlled, they begin to form, and you see a dramatic decrease in the shelf life of a product because of that oxidation. And then a third case of autooxidation would be different reaction mechanisms in the body. There's a nice page talking about the liver toxicity of acetaminophen, and how that occurs through a radical process. So in the example here, we have cumene reacting with atmospheric oxygen at the benzylic position to form a hydroperoxide. And usually this process is slow. Let's look at it in a little more detail. So in this mechanism, there are two things I want to focus on. One is our definition of initiation, propagation, and termination. I'll come back to that. And the other is just what's actually taking place in the reaction. So we have a free radical initiator leading to the abstraction of a proton and creating our alkyl radical. This can then react with oxygen and drawn as a resonance diradical structure, form through coupling, but maintain the radical. So this is not a termination step. This is a propagation step. This radical can then abstract a hydrogen to give us a hydroperoxide and regenerate our radical species. And this can go on, or that radical species can terminate, and we go from 2 radicals to 0 radicals. So that's a termination step. We call this the initiation, but this is actually a propagation step. We have a radical initiator on the reactant side, and we have a single radical on the product side. So the definitions that I've been using about a change in net radical number, this is a propagation step, and that's what I want you to remember. If you haven't been paying attention to that, you may have been thinking that anytime there's homolytic bond cleavage, that's a radical initiation step, and that is not always the case. So we can define our propagation steps as those steps that, when summed, give us our net chemical equation. So from the previous slide, our 2 coupling steps were the alkyl radical reacting with the diradical oxygen, and that radical, that coupled radical, uh, reacting to abstract a proton and give a hydroperoxide. So our net reaction is our alkyl compound plus oxygen gives us a hydroperoxide. So these are both propagation steps. So I mentioned that ethers are particularly susceptible to autooxidation. Diethyl ether will form explosive hydroperoxides. Um, Most laboratories will have a standard operating procedure for labeling ether when it's opened and discarding it after a defined period of time. And sometimes this results in discarding nearly the entire quantity in the bottle if no one has used any. But that's required for safety. I have met in my lifetime a person that was in an ether laboratory explosion. It's not as common as it used to be. We understand that that is engendered from exposure to light and oxygen. So we store these compounds in dark containers to prevent light from accelerating that autooxidation process. For those of you in my lab class, this is the issue that caused the change in the lab schedule. When people started taking classes remotely, our ether supply was discarded because it had reached its allowable storage period after being opened. And we didn't want to purchase additional ether because it seemed likely that it would be discarded. So now we're resupplying with ether and struggling with supply chain issues. So our schedule may continue to be impacted based on our expected delivery date. Another place where autooxidation is significant is in triglycerides. So you need triglycerides in a healthy diet. These are susceptible to autooxidation. If you fry foods, water will enter the oil from the foods, and this can also accelerate the oxidation. So a jar of peanut oil on a grocery store shelf may last for years, but after being used once, that oxidation process is initiated, and within a few weeks, used oil will turn rancid. One of the things we can do to try to control that autooxidation process is to use radical inhibitors. So you may be familiar with BHT, butylated hydroxytoluene, or BHA, butylated hydroxyanisole. If you go to a vending machine and you get a bag of chips, read the label carefully. There's a good chance that it will contain one or both of these free radical scavengers. So these inhibit free radical oxidation by forming stable free radicals. And just something I'll mention, won't come up in our class, but if you look at the polarity of this structure, this is quite a non-polar molecule. So this is quite fat soluble, soluble in organic solvents. But if you had a hand cream that had unsaturated fatty acids, you would not be able to achieve any appreciable level of BHT in the aqueous fraction of the hand cream. So a molecule like BHA, which has much greater water solubility, would be a preferred antioxidant in an oil and water emulsion than BHT. One molecule of BHT prevents thousands of autooxidation reactions. BHT undergoes hydrogen abstraction, and this resonance stabilized structure is quite stable and doesn't propagate the oxidation reaction. There are several natural antioxidants. Vitamin E, which is tocopherol, prevents a number of oxidations in the body and cell membranes. Vitamin E is hydrophobic. It's able to get into cell membranes. It collects in fatty tissues. If I don't recommend taking mega doses of vitamin E, but studies have been done. People that do that uh, accumulate very high levels of vitamin E in their testes. It's not doing a lot of good there, but that's where it accumulates. Vitamin C, ascorbic acid, functions as an antioxidant and quite water soluble. So it functions in blood as an antioxidant.